Circle. Introduction. Basic concepts of circle. The set of points equidistant from a fixed point in a plane is a circle. We are familiar with the concepts regarding circle like center, radius, diameter, and chord. The fixed point is called the center of the circle and fixed distance is called the radius of the circle. Radius is also the segment joining the center and any point on the circle. In the circle, O is the center of the circle and segment OP is the radius. Circle can have infinite radii. Radii of the same circle are congruent. A chord is a segment whose ends lie on the circle. In the figure, segment AB is the chord. Circle can have infinite chords. The chord which passes through the center is the diameter. Diameter is the longest chord of the circle. Diameter is twice the radius. A circle can have infinite diameters. Let's recall. 1. A perpendicular drawn from the center of a circle on its chord bisects the chord. In the figure, if O is the center of the circle, segment OM is perpendicular to chord AB and M is between A and B, then AM is equal to MB. 2. The segment joining the center of a circle and the midpoint of its chord is perpendicular to the chord. In the figure, if O is the center of the circle, M is the midpoint of chord PQ, then segment OM is perpendicular to chord PQ. That is, angle OMP is equal to angle OMQ is equal to 90 degree. 3. Congruent chords of a circle are equidistant from the center of the circle. In the figure, O is the center of the circle. If chord AB is congruent to chord CD, segment OM is perpendicular to chord AB and segment ON is perpendicular to chord CD such that M is between A and B, N is between C and D, then OM is equal to ON. 4. The chords of a circle equidistant from the center of a circle are congruent. In the figure, O is the center of the circle. Segment PQ and segment RS are chords. Segment OM is perpendicular to chord RS and segment OM is perpendicular to chord PQ such that M is between R and S, N is between P and Q. If OM is equal to ON, then chord PQ is congruent to chord RS. Remember this. Infinite number of circles can pass through one point. Infinite circles pass through two equidistant points. There is one and only one circle passing through three non-collinear points. No circle can pass through three collinear points. Secant and tangent. In the given figure, not a single point is common on line L and circle with center A. Point P is common to both, line M and circle with center B. Here, line M is called a tangent of the circle and point P is called the point of contact. 2 points Q and R are common to both, the line N and the circle with center C. Q and R are intersecting points of line N and the circle. Line N is called a secant of the circle. Let us understand an important property of a tangent from the following activity. Activity. Draw a sufficiently large circle with center O. Draw radius OP. Draw a line AB perpendicular to segment OP. It intersects the circle at points A and B. Imagine the line slides towards point P such that all the time it remains parallel to its original position. Obviously, while the line slides, points A and B approach each other along the circle. At the end, they get merged in point P, but the angle between the radius OP and line AB will remain a right angle. At this stage, the line AB becomes a tangent of the circle at P. So it is clear that the tangent at any point of a circle is perpendicular to the radius at that point. This property is known as tangent theorem. Tangent theorem. Theorem. A tangent at any point of a circle is perpendicular to the radius at the point of contact. Given Line L is a tangent to the circle with center O at the point of contact P. To prove, line L is perpendicular to radius OP. Proof. Indirect method. Let us assume that line L is not perpendicular to the segment OP, then let segment OQ be perpendicular to line L and let point Q lie on line L. P and Q are different points. Take a point R on the line L such that Q is between R and P, so QR is equal to QP. Draw segment OR. In triangle OQR and triangle OQP, segment OQ is congruent to segment OQ. Angle OQR is congruent to angle OQP. Segment QR is congruent to segment QP. Triangle OQR is congruent to triangle OQP. Therefore, segment OR is congruent to segment OP. Therefore, OR is equal to OP. But segment OP is the radius. Therefore, segment OR must also be radius. Therefore, R lies on the circle. That means line L intersects the circle in two distinct points, P and R, but line L is a tangent. Therefore, it intersects the circle in only one point. Our assumption is that line L is not perpendicular to radius OP is wrong. Therefore, line L is perpendicular to radius OP. Converse of tangent theorem. Theorem. A line perpendicular to a radius at its point on the circle is a tangent to the circle. Given M is the center of a circle, segment MN is a radius. Line L is perpendicular to segment MN at N. To prove, line L is a tangent to the circle. Proof. Take any point P other than N on the line L. Draw segment MP. Now, in triangle MNP, angle MNP is equal to 90 degrees. Therefore, triangle MNP is a right angle triangle. Therefore, segment MP is the hypotenuse. In a right angle triangle, the hypotenuse is the largest side. Therefore, segment MP is greater than segment MN. Therefore, segment MP is greater than the radius. As segment MN is radius, point P can't be on the circle. Therefore, no other point except point N of line L is on the circle. Therefore, only point N is the common point between line L and the circle. Therefore, line L intersects the circle in only one point N. Therefore, line L is a tangent to the circle. Remember this. A circle can have infinite number of tangents. One and only one tangent can be drawn at a given point on the circle. No tangent can be drawn from a point in the interior of the circle to that circle. Two tangents can be drawn to a circle from the point in the exterior of the circle. Tangent segment theorem. In the figure, two tangents PQ and PR are drawn from an external point P to the circle with center O. Segment PQ and segment PR are called as tangent segments. Theorem. Tangent segments drawn from an external point to a circle are congruent. Given a circle with center O, lines PQ and PR are tangents to the circle at points Q and R respectively. To prove, segment PQ is congruent to segment PR. Construction. Draw segment OP. Draw radius OQ and OR. Proof. In triangle OQP and triangle ORP, angle OQP is equal to angle ORP is equal to 90 degree. Hypotenuse OP is congruent to hypotenuse OP. Side OQ is congruent to side OR. Therefore, triangle OQP is congruent to triangle ORP. Therefore, segment PQ is congruent to segment PR. Examples. 1. In the figure, O is the center of the circle. From point R, segment RM and segment RN are tangent segments touching the circle at M and N. If OR is equal to 10 cm and radius of the circle is equal to 5 cm, then 1. What is the length of each tangent segment? 2. What is the measure of angle MRO? 3. What is the measure of angle MRN? Solution. Draw segments OM and ON. 1. In triangle OMR, angle OMR is equal to 90 degree. Therefore, by Pythagoras theorem, OR square is equal to OM square plus MR square. Therefore, 10 square is equal to 5 square plus MR square. Therefore, 100 is equal to 25 plus MR square. Therefore, MR square is equal to 100 minus 25. Therefore, MR square is equal to 75. Therefore, MR is equal to square root of 75. Therefore, MR is equal to 5 square root of 3 centimeter. RM is equal to RN is equal to 5 square root of 3 centimeter. Length of each tangent segment is 5 square root of 3. 2. In triangle RMO, angle OMR is equal to 90 degree. OM is equal to 5 centimeter and OR is equal to 10 centimeter. Therefore, OM is equal to half of OR. Therefore, angle MRO is equal to 30 degree. Similarly, angle NRO is equal to 30 degree. 3. Angle MRN is equal to angle MRO plus angle NRO. Therefore, angle MRN is equal to 30 degree plus 30 degree. Therefore, angle MRN is equal to 60 degree. Answer. Length of each tangent segment is 5 square root of 3 centimeter. Angle MRO is equal to 30 degree and angle MRN is equal to 60 degree. 2. What is the distance between two parallel tangents of a circle having radius 4.5 centimeter? Justify your answer. Solution. Let the center of the circle be O. Let the tangents AB and CD touch the circle at point M and N respectively. Draw segment OM and segment ON. Through O, draw line XY parallel to line AB. Line AB is parallel to line CD. Line XY is parallel to line AB. Therefore, line AB is parallel to line XY is parallel to line CD. Angle OMA is equal to angle ONC is equal to 90 degree. Line AB is parallel to line XY and line OM is a transversal. Angle AMO plus angle MOX is equal to 180 degree. Therefore, 90 degree plus angle MOX is equal to 180 degree. Therefore, angle MOX is equal to 180 degree minus 90 degree. Therefore, angle MOX is equal to 90 degree. Similarly, angle NOX is equal to 90 degree. Therefore, angle MOX plus angle NOX is equal to 90 plus 90 is equal to 180 degree. Therefore, angle MOX and angle NOX are adjacent as well as supplementary. Therefore, angle MOX and angle NOX form linear pair. Therefore, ray OM and ray ON are opposite rays. Therefore, points M, O and N are collinear. Therefore, MN is the distance between the parallel tangents AB and CD. MN is equal to 2 into radius. Therefore, MN is equal to 2 into 4.5. Therefore, MN is equal to 9 centimeter. Answer. Distance between parallel tangents is 9 centimeter.